Hello students of B.Sc.TY student, semester 5, and our paper is linear algebra, 13th paper. Our lecture is the 9th lecture. Today we are going to discuss what is the subspace of a vector space. Subspace of vector space. So in third and fourth semester we have discussed some concept like the group, ring, and in 9th and 10th standard we studied what is the set. Then there is a next concept is subset, ring, subring, group, subgroup. Like that we are going to discuss subset of a vector space, and that is called subspace of vector space. Because vector space is a set, so definitely it has a subset, and that subset is called subspace. We discuss definition. See here, if V is a vector space over the field F, V is any vector space over the field F, and W is the any subset. W is subset. This W is a subset of the vector space V. Then W is a subspace of V. So any subset W of the vector space V said to be subspace of V, and W itself form. So what will be necessary things? So W itself forms a vector space over the field F. Definitely this definition is like group and ring. So what is the subgroup? If H is the subgroup of group Z, then we have already discussed the H itself form group. So in similar manner, if W is a subset of the V, then W itself form a vector space over the field F. Or we can give one alternate here definition. One algebraic definition is given. So W is a subspace of the V whenever two elements omega 1, omega 2 belonging to W and alpha beta belonging to the field F, then alpha omega 1 plus beta omega 2 must be belongs to W. So here V is any vector space, and W is a subset. So if V is a defined, V is a vector space over the field F, then this W is also a vector space over that field F. Same field for W and V. And with respect to that field, this W must have to form a vector space. Then W is called vector subspace or subspace of vector space. Subspace of vector space. Or other definition is that, equivalent definition, if we choose any two element of W and alpha beta be the any two element of the field F, Then if we multiply to alpha omega 1 plus beta omega 2, so this element must contain in the W. Then this W is called subspace of vector space V. So in previous lecture, we have discussed, already we have discussed on some examples of vector spaces. From that we pick out one example, and that is, see this example. Let V be a set of polynomials in X without restrictions of degree of polynomial, and we discuss one example Vn with a set of polynomials in X of degree less than n. There is a restriction less than n. So this less than n degree, this set Vn is a subspace of the vector space V. This is a very first class example. You can also verify it. What is V? V is a set of polynomials. I write it as P of X, set of polynomial, such that P of X is polynomial like this: alpha naught, alpha 1x, alpha 2x square, and so on. No restrictions of for all the alpha belonging to the field F, and there is no restriction on degree of the polynomial. And Vn be the other set of polynomials, that is Q of X, such that, and Q of X is alpha naught, alpha 1x to alpha n x power n minus 1. Sorry, n minus 1 is given, such that for all the alpha I belong to field F. And what is I? I run from 1 to n minus 1. So this set of polynomials, and this is a vector space. We have already proved this. This is a vector space. So this is a vector space of the polynomial of degree less than n. So that is n minus 1. And this is a vector space. This is a vector space of the polynomial having no restrictions about their degree. So this region is subspace of vector space V. You can verify. If we choose the any alpha, and if we choose the any beta belonging to field F, and choose any polynomial from this set, polynomial having degree less than n. So if P of X be the any element, and plus, that means there is any, we choose any polynomial, suppose Q1 of X, Q2 of X, and so on. So if I choose Q1 of X and beta into Q2 of X, so then we get again a polynomial less than n minus 1, less than degree n. So if alpha into polynomial less than degree n, alpha into polynomial less than degree n, beta into polynomial less than degree n, then their sum also belongs to this is Vn, also belonging to that set having degree less than n. Definitely. So students, some more and more examples are given at the end of our chapters. You try to solve some more problems, and if you have any difficulty on about any problem, then you can ask me your difficulties. Now we are going to discuss next definition, and that definition is homomorphism. what is meant by homomorphism. So in third and fourth semester, we discussed what is meant by homomorphism of group, and in fourth semester we know that what is meant by homomorphism in ring. So similarly, in similar sense, we have to study what is meant by homomorphism in vector spaces. So student, I write here a definition. If U and V are vector space over field F, are vector spaces over field F, that is U be the vector space over field F and V be the vector space over field F. Both are defined on the same field. Then the mapping T, we take here mapping T of U into V, U into V is said to be homomorphism. Is said to be homomorphism. If is said to be homomorphism. U be the any vector space, V be the any vector space defined on the same field F. U vector space defined on F, V vector space defined on F, and T is a mapping from U to V. Then this mapping is called homomorphism if some points are there, and first point is U plus U2 and this T. So this UT, U1T plus U2T. That means any two elements, this U1 and U2, belong to capital U, and its image under mapping T can be U1T plus U2T. And second, alpha U1T is equal to alpha U1 for all U1 U2 belongs to U and alpha must belong to field U. So here where revise it. If U and V are a vector space over the field F, and then there is a mapping T, of the U into V is said to be homomorphism if image of U1 plus U2 under T is U1T plus U2T, and image of alpha U1T is equal to alpha U1T for all the U1 U2 belongings to the U and alpha belonging to the field F. If these two conditions satisfy, this and this, then the mapping is said to be homomorphism. So by schematic representation, we can represent it in this way. Suppose this is a set U, this is a set U, and this is a set V. And there is a mapping T such that U into V mapping. So this element, this is a U1, this is a U2, this is a U3, this is a U4, and so on. Some elements are there, I don't know. And here V1, V2, V3, V4, V5, like this, there are some element. So image of u1 plus u2, what is given that? So u1 plus u2, whatever the u1 plus u2 and its image is similar to image of ut1 plus image of u2t. If this condition satisfies, that means u1 u2, there is a element u1 plus u2, this is a element u1 plus u2, because u is a vector space. So sum of any two element again belonging to the u. So if u1 is there, u2 is there, so u1 plus u2 100% is there. 100% u1 plus u2 is there. So image of this, if we directly count, if we directly take the image of this u1 plus u2, so this u1 plus u2 image is equal to image of this. Suppose this is image of this u1t and u2 image of u2 is u2t. That means u22 is v2 and u1t is v1. These are element of v, therefore we indicate is v1, v22. Actually v1 is image of u1, and therefore we can write this like this: u1t is equal to v1. That means image of u1 is v1. So u1 is in u, u2 is in u, then u1 plus u2 in u. So if we are going to finding the image of u1 plus u2, so it is the same, and there is a v1 plus v2 element also, and that v1 v2 element is nothing but u1t plus u2t, that is v1 plus v2. Remember, in group theory, in ring theory, we are frequently discussing this. This schematic representation is not, it is not unfamiliar to all of you. Okay? Definition of homomorphism, it is not unfamiliar to all of you. It is familiar. But we are going to discuss in a different cases. Homomorphism in group, homomorphism in ring, and homomorphism in vector spaces. All are analogous. All are similar. So student, I hope you understand this, what is meant by homomorphism in vector spaces. So in next lecture we will discuss some definition and one lemma. So thank you very much.